Thank you very much, and thanks to everyone for attending today's webinar. Uh, Basically, quantum computing is poised to pave the way for some groundbreaking technical achievements across almost all verticals. There's a lot of fear and uncertainty and doubt and questions. Obviously, there's some hard physics and science and some math and some computer science kind of all being melded together. We're basically trying to help clear up a lot of the confusion in this. So let's talk about what we're going to go over today. Again, as Brett said, we're going to go for about 30 minutes or so. We're going to save the bulk of the time for questions. So please, as you get a question, do type it into the WebEx system, and we'll get through as many of those as possible. If I see that there's a lot of questions, I might try to speed things up a little bit so we can get through more of them at the end. If your question is not answered, you can feel free to email me at whurley, W-H-U-R-L-E-Y, at IEEE.org, and I will try to answer your question at some time in the near future. So for today's agenda, we're going to do a very high-level overview of quantum computing. I do want everyone to understand that we are approaching this as if most of the people here already have at least a baseline level of quantum computing and understand what it's about, because we are focusing on the standards effort. We're going to go over the current state of the industry. It's nascent, it's fractured, give you a little bit of specs and data on that, look at some of the challenges faced by the industry, and then we're going to look at two of the IEEE proposed solutions that we have, which is IEEE P7130 and P7131. Then we'll talk about who's involved in those projects, how they're involved and what they're doing, what the goals of the projects are, and then we'll talk at the end about how you can get involved with both of these standards. And we would encourage you to, and I'm going to say this several times, but as a foreshadowing, these are corporate standards, so you have to be involved through a participating company. So your company has to be a member of the IEEE for you to be able to participate. Just want to make sure everybody's clear on that. So with that, we'll move along. Quantum computing. Basically, there's a couple things we want you to be thinking of as we talk about this in the frame of standards. It takes advantage of quantum mechanics. Obviously, if you think about the processor in your phone, there's billions of transistors on there, 3 billion on the new Snapdragon chip, and things are getting smaller and smaller and smaller. So one thing people often talked about is at what point does it get small enough that things like quantum tunneling come into play? We can no longer impede a flow and have a 1 or a 0. All of the research in the labs for the last 30, 40 years has led up to the moment we're at right now. And basically, these computers take advantage of superposition and entanglement. As we said, we assume you have a baseline knowledge of that. And we think that they should be looked upon as a coprocessor or cloud processor. It's really important to stress that these are not a replacement for classical computers. In fact, they are dependent upon classical computers for the cryogenics management, the systems management, the FPGA management, getting the data from a computer into a quantum computer, cooling it down and managing that process, processing it and putting it back out, are all things that you need a classical computer for. So while you may read in the popular press about things like, the quantum apocalypse, and we'll talk about that in a little bit, and how quantum computers are replacing classical computers, I would approach this as thinking of them as more as a coprocessor, cloud processor, and I think that would be very beneficial. So moving quickly on, why are we looking at doing a standard? So give you a little bit of background about where the industry's at. In 2015, as you can see on your screen, there was billions of dollars being pumped into research in quantum computing by all of the governments you see. Now, China has made the most progress in this, last year investing 10 billion into a 92 hectare facility for quantum research. The United States is seen as often as being a little bit behind. Japan, Netherlands, some others have really picked up the pace in their research. But between 2015, when these numbers were taken by McKinsey, and today, that has almost tripled across the board, and a bunch of new companies have entered the picture as well, countries have entered the picture as well. So there's a lot of activity going on in the research that can be seen publicly. This does not include in any of these numbers any private, secret projects or government projects that aren't publicly available. So that's been picking up quite a bit. And around 2015, you see an influx in a couple of things. If you look at the patent applications in that same year, you see that the United States had almost 300 patents, but you also see that Canada, Japan, Britain, China, Australia, Germany, South Korea, Israel, and Finland all had also filed patents. And if we take a closer look into that, then we can see that from 2003 to 2014, the interest in quantum computing and patenting applications of quantum computing had 17% year-to-year growth. Now, patents aren't always the best way to judge the inflection point of a product development or technology development. But if you look at the fact that around 2014, you had the increase in investment go up dramatically and continue to go up. You had the numbers of patents filed continue to go up. And you look at those patents across families, then you see that, both in the patents specific to qubits and hardware and apps, you see an increase in all of these around that same time. Tie that into venture capital funding, tie that into the news, kind of the buzz or hype cycle, if you will, then you can see that quantum computing is clearly reaching an inflection point. Now, does it continue on to where we have a general purpose quantum computer? Does it continue on to where we have some of the things that we all hope and dream we'll have? To be determined, but clearly there's an inflection point, and that's where the need for standards is coming from, because when we look at it, there are a lot of challenges in the industry. Now, before we move to those challenges, I want to talk for a moment about the Google trends. I think you find it very interesting if you look at the trends worldwide for quantum computing back in 2004 being very high and then dipping down considerably from that peak of 100 to about 20 for several years and then popping back up again in 2016 and 2017. So this is very telling because when you look at the patents, when you look at the VC funding, when you look at the companies and the countries that are funding these efforts, then you see an inflection point. But when you look at the searches of Google in Zeitgeist, you see that we had a lot of interest, we lost a majority of that interest, and now we're getting that interest back again. And I think the reason that you see this is because in 2004, we had some of the same problems that we have now in 2016. Again, we feel this is a real need for why we need to have a standard. Because when you look at the public, when you look at your CTOs, your CIOs, your engineers wanting to work with the technology for quantum computing, geneticists, mathematicians, et cetera, there is a lot of confusion out there about quantum computing in general. So let's talk a little bit about that. I'm going to spend a considerable amount of time on this slide, but basically definitions for quantum computers, qubits, all of the various technical things are very confusing. There's basically three types of quantum computing we'll focus on today. There are more than three ways to build a quantum computer, but the primary items that are in the market are annealing, which is D-Wave's primary technology, the circuit gates, which IBM, Google, and Rigetti are working on, and topological quantum computing. Now, when you think about that, um, that already can be pretty confusing to someone not familiar in the art. What is an annealer? How does it work? What's the difference in a circuit gate model? What's the difference in a topological quantum computer? And at a very, very high level, annealers, similar to metallurgy, D-Wave has had those out commercially for quite a while. They've got a lot of patenting in that area. Professor Nishimori and Sid Lloyd kind of created that technology, and there's often the discussion of, should it have been patented or not. But D-Wave has been really focused on achieving, the maximum efficiency they can and doing things like optimization and things around that, like with the annealers. They're in use at, NASA Ames, at the AI lab. They're in use at Volkswagen for doing traffic research and dozens of other companies. The second type, circuit gate modeling, works a little bit more like you'd think a computer works, using gates. IBM has started last year with a 17 qubit machine, which was a big deal, and then moved by the end of the year to a 50 qubit machine, which they have also made available, and they have been very quickly commercializing this technology. Google started this year with a 72 qubit chip, and then Rigetti is still around 19, but they've been doing very, very interesting work. in the area of machine learning and quantum computing, and making a lot of progress. So when you look at that, there is uh, right there, without including ion traps and everything else, three very distinct architectures that are involved. The last, of course, being the topological by Microsoft. Microsoft has been using topology to create what they call a topological qubit. Now they have need to discover an anion. There's a lot of very hard physics that once they happen, then this will come into being. But that makes even more confusing. And the reason that is because if you go to D-Wave's website, you'll see that D-Wave has 2,048 qubits in their latest machine. Now, if I'm a consumer of quantum computing and I have 2,048 qubits, and then IBM says, oh, we've just made this major achievement, we have 50, Google has 72, and they're kind of related, but then Microsoft is out there saying, well, one topological qubit could be comparable to thousands or hundreds of thousands or millions of other qubits because of the way it works in the architecture we've chosen. It can be incredibly confusing. It doesn't matter if you're a software engineer, it doesn't matter what role is, you're a software engineer, a hardware engineer, you're a consumer, you're a CTO, you're a CIO, obviously right there at a base level, that can be very, very confusing. And so, when you look at this, vendors are kind of saying, obviously insert our technology, our architecture is the best architecture for quantum computing. And, researchers, say, well, sure, if you don't want to use one of the 9 other ways, you don't want to use ion traps, you don't want to use optical tweezers, any of these other ways. And there are several companies that are funded using both of those technologies to create quantum computing. So again, more and more and more and more confusion. So then you have investors, they're very confused in the market. Call us back when you have something, let us know. Now, why do I harp on investors so much throughout this, deck? Look, we need investment for the people that want to take this technology forward to be able to do stuff. That investment can primarily come from three places. It can come from governments who want to fund research areas, national labs, or DARPA or ARPA or projects like that. It can come from companies like IBM and Microsoft hiring engineers to work on this, investing money, developing it, or it can come from venture capitalists in the community. And those are probably the primary three ways that this industry gets funding, and it does need funding. But there's a chicken and the egg that we need to all be aware of. It does not get the funding if we do not have some tangible proof of the value of it, or something that's showing a leaning towards a market adopting it. And right now, although you'll see hedge funds like Two Sigma and others playing around with quantum computing, you see Volkswagen playing around with quantum computing, you don't really have a lot of people doing work in this area that's seen as, earth-shattering, groundbreaking, kind of fulfilling those promises that have been made by the quantum computing community. That's incredibly, incredibly important, because I think that you can directly correlate the lack of adoption across the board in places like pharma and finance and energy directly to the fact that if I go and I speak to a CIO, if I go and I speak to a CTO, they are confused on the technologies, the type of technologies, how many qubits there are, how it works. And then of course there's plenty of videos on the internet saying, what would we use a quantum computer for? What could be done with it? And these businesses, these people that will be the adopters of this technology, they want those questions answered, and they want those questions answered before that they've invested the potentially millions of dollars that many are asking them to present. So with that, and if I can get to this slide, there we go. There's another challenge, benchmarking. So for years, D-Wave, and we're not beating up on them. Bo Inwald, who's the president there, is a great guy and who's part of this standard initiative we're talking about. But for years, if you go in the press as an objective observer, as a CTO or CIO, you will see D-Wave publish papers that show the advantages of quantum annealing on optimization problems and others. And you will see people, professors at universities, et cetera, come out and publish papers that say that they can disprove those papers. They can debunk those claims that quantum computer is faster. Part of the reason that I wanted to get involved with the quantum computing standards is to introduce a standard around benchmarking. I think we need objective ways to, once we've solved the nomenclature issue, we need objective ways to solve the is this actually valuable to my business question. Again, using that same kind of philosophy in the last, vendors ask, our new quantum computer is a gazillion times faster than your classical computer at something, maybe we think, run the process again and again. They have no third party, no objective way of validating those claims. Researchers often come out and post that they are not true, that these claims can be easily disproven, and that makes what? That makes investors, whether they're government, whether they're companies doing projects, or whether they're venture capitalists, say, well, hey, maybe we should wait a bit longer. And so, then you have our consumers that we're concerned about, which are asking all of us. And I've just spoke at a South by Southwest keynote, at Mercedes keynote in Europe late last year, and about a dozen others in the last 6 or 7 months. And the number one question I get is, kind of like Office Space. So what exactly would you say you do here? This quantum computing thing sounds interesting, but what does it mean? How is it advantageous? How do I know how to navigate this? And so with that, we'll jump right into what we're proposing as the IEEE's solutions to help address these two primary issues, which can best be separated into an issue of nomenclature and standards around the language we use to talk about things like quantum computing and the architectures and the qubits, and performance benchmarking and testing and validation of that benchmarking. So the first standard that we've proposed is IEEE P7130. So the working group is the new quantum computing working group. The sponsor is our corporate advisory group, and then the society is the IEEE-SA Board of Governors that have helped make this into this PAR that we hope to take and ratify as a standard. I've put a link on there. We'll make sure that this is available as well. But if you go to the IEEE standards site, you can simply search for P7130 and find it, or you can use this link, which is standards.ieee.org/develop/project/7130.html, and you can learn more about the project. If you're interested in participating, again, you can email me at whurley, W-H-U-R-L-E-Y, at IEEE.org. I can help guide you through the process. Whether your company is a member or not, I can give you all of the guidelines, and we have people that can help your companies become a member should this be something that you want to participate in. And when I say companies, your organizations, it could be university, it could be anybody. So what is this standard about? Well, this nomenclature standard is about pulling up the definitions for all of the components, not the physics definitions. We're not going to redefine superposition. We're not going to redefine entanglement. Those are already done, but we are going to very well define qubits, very well define the various types of architectures within quantum computing. So a lot more detail on topology, a lot more definitions around, the components of topology. Same thing with annealers, even though those have been out for a while. We need to have everyone be able to agree on that, and especially in the circuit gate modeling, which seems to be, probably the fastest growing area. Having these definitions, having something that people can go to, that they can look at, that says, okay, we now understand what it is that you're trying to talk about when you say, I'm using an annealer that has 2048 qubits. I, as an engineer, as a developer, as a customer, know what you are trying to say and understand it in the same level that you do. This is incredibly important. In these keynotes I've been going out and giving and the work I've been doing with the IEEE to get this standard to this point, we have talked to hundreds of people, and to say that there is confusion around the terminology that is used is absolutely an understatement. People are completely lost when it comes to a lot of what we're saying, how we're saying it, what we're doing. So we really feel that this standard is vitally important to pushing things forward. So again, that's P7030, standard for quantum computing definitions. And again, the purpose is to provide a general nomenclature for quantum computing that can standardize communications between all projects. We will have hardware and software covered in this. This is also very confusing. As a software developer, I myself have fallen victim to this when I try to work with a hardware vendor and I make the assumption that when they say X, Y, and Z about their quantum architecture, they mean the same thing that another one I'm already working with says, only to find out that they don't. So having these standards, I think, is going to be vitally important to what we do and to how we do it. So moving on, our second proposed solution is PAR 7131, which is a standard for quantum computing performance metrics and benchmarking. Again, we have the same working group, sponsor, and society. And again, I've put the link up. It's the same standards.ieee.org/develop/project/7131.html, or if you go to standards.ieee.org, you can simply search for 7131 and it will pop up at the top. This one is going to be probably more contested than the first. When it comes to the nomenclature, we went out, we talked to about 30 companies and universities, and everybody agreed that we need that. And while there will be some contention on how we define certain things, we'll work through that in a collaborative fashion. Everyone agrees that we need that one. When you come to performance benchmarking, uh, all of the users agree that we need it, not necessarily everybody else agrees. And the reason is that performance benchmarking and having a standard performance benchmark will be unbelievably important to actually finding out exactly how much faster, how much benefit, how much of an advantage I get by using a quantum computer, either in a standalone format or again, as I propose, as a coprocessor / cloud processor. So that basically is incredibly important because there has to be a demonstrable way in which we can show the advantages of quantum computing in an objective format in a way that consumers can understand and know what they're getting without us being every time that you go out, you see, there is a quantum computer, they claim it's a million times faster, and then there's a professor who says that actually they could do the same thing on their laptop. The reason this confusion sets in, the reason this is needed is because a lot of times the quantum computing manufacturers will customize solvers for the quantum computing and not optimize the solver on the classical architecture that they're comparing to. There's a lot of examples of this everywhere. And so we feel that by having this standard and by having a set of benchmarking processes that people can all adhere to, we can actually start having the manufacturers of the hardware and the makers of the software collaborate in a way where you can see which machines are fastest, which machines are performing the best, again, around a standard set of tools and methodologies. So again, to sum up, PAR 7130 is our standard for quantum computing performance metrics and performance benchmarking. You see the summary of the project there, which is to provide a standardized set of performance metrics and standardized methodology for benchmarking speed and performance across all of these types of hardware, as well as comparing these to each other and to classical machines. So we're very excited about both of these, and we're very excited about who's participating in both of these, and I'd like to talk about that for a moment before we move into some Q&A here in a few minutes. We have a very strong showing of companies that are getting behind this. IBM has come to the table and been very helpful. Jerry Chow and Jay Gambetta there, along with Bob Suter, are very supportive in this effort to build standards in an open collaborative fashion. Again, Bo Inwald, president at D-Wave, has been very tremendously helpful in getting us to this point and in helping bring not just the annealing knowledge, but his extensive knowledge and credibility in this area. So we're very happy to have both of them involved. My company, Strangeworks, is also participating. We're chairing the standards committee and we're helping collaborate with all of these people. We're counting the startup area, not in the corporate area. And Rigetti, which is probably one of the hottest startups in quantum computing, who's making both hardware and software in this area. Will Zhang there is participating. Very well known, incredibly good speaker, incredibly good physicist, and all around great guy who is working on very, intensely on a daily basis with both the hardware and the software. and a lot of customer problems. So we're very excited to have Will and Rigetti on board as well. And then, of course, some of my favorite people in quantum, One Qubit, Canadian company, Andrew Fersman there, just probably one of the best people to know in quantum, along with Will and Bo. And Andrew has been very generous with his time in helping us get these things to the point to where we can make a proposal, knowing that we can move forward and that we can execute on them. So that it does not mean we're limited. These companies are input. There's 147 of you online right now. I'd love to find a way to get all of you, as many of you as possible, involved. And we have several other companies right now that are going through the process of getting their corporations into the IEEE Standards Association as members and getting their assigned delegates to participate. So this group is expanding, but this was a really strong start to have the 5 of these companies collaborating this, representing both the hardware and the software and a lot of customer input. So we're very, very, very excited about that. Um, so let's talk for a few minutes about how you can get involved. It's very easy. Again, it does require corporate participation. That does cost money, but that is not hard. If you email me, whurley, whurley@ieee.org, I will be more than happy to help guide you through that process should your company want to participate. You can only represent your company once a company is a member and once your company has said that you are the person that we want. We've had a couple of companies where people approached us, the company got involved, and the company wanted somebody else to represent them. That all is the internal policies and procedures of your company, so I trust that you'll know those better than me, but we can help you get into this, and we do want your help on this. It's important that both the nomenclature standard and the standard around performance benchmarking have as much input from our community of engineers as possible so that we can move quantum computing forward by getting everyone to use the same language and by getting everyone to use the same metrics when they're making claims about their machines. So with that, it looks like I finished almost exactly about 3 minutes earlier than I had planned. We'll move into the questions and answers. I think, Brett, you're going to moderate those, so I'll hand it back over to you.
All right, great. Thank you very much. Thanks for your presentation. Appreciate it. We have a lot of questions, so we'll get right into it. We'll start high level. We had a question asking, should I start my research in this field? So I guess in thinking about investors investing in companies, this person's thinking about investing time. So I guess the quick pitch for quantum computing and the true power of it.
Yeah, and I'm putting an answer in there. Arun, that's a great question. I get asked that a lot. The answer to that question is yes, I think this is a great time to start your research in this field. People have been doing this research in this field for quite a long time, but as I said, around 2014, we started seeing an inflection point. And just because it's taking off, just because there's hundreds of patents being filed, because there's billions of dollars being invested, because there's a lot of new startups in the area, doesn't mean that it's not ripe with opportunity. There are an innumerable amount of problems and questions and things that haven't been answered, that you can get involved with. I would say, yes, it's a good time to start your research in this field, but I would also temper that and say you might want to decide what you want to research in this field. Are you going into cryogenics for the circuit gate models or the annealers? Are you looking at, getting a head start on topology? Are you looking at software versus hardware? So I would make sure that you look at a lot of the data and do that. And there's a couple of other projects I'm associated with that might be useful. If you go to quantumcomputing.stackexchange.com, we've created an open community site for questions and answers about this, and maybe reading some of that or reading some of what we're doing, joining some of the standards meetings might get you to a point where you know something specifically you might want to research on.
Okay. I have a question from a research scholar, and they're wondering how you could possibly incorporate quantum computing in cloud security.
So that's a great question. If you think of the thing when we talk about quantum computing and security, everybody always brings up Peter Shor and Shor's algorithm. One of the things that isn't often brought up about that algorithm that I find very interesting is how much of it is actually quantum. Now, I want to temper that with obviously there's a lot of quantum magic, but if we look at Shor's algorithm, okay, and taking something like breaking the RSA encryption or whatever, while that's super interesting, there's only one step that's really quantum, right? So for those of you who aren't familiar, we'd basically look if n return, is even and returns a 2, so we'll make sure it's an odd. If it isn't, then 2 is a factor. If it's not odd, the end of file. Then we check, for n equals a to b, for a greater or equal to 1 or b greater or equal to 2, and we return a. So we're checking that n is the product of two co-prime numbers in the second step. Then we move to the third step, where we take a random number and check that it's not a factor. If it is, again, kind of an end of file. And then that's where the quantum step comes in, because those all have classical algorithms to do that, but there's no classical algorithm to do the order finding when you order find r of x to the k mod n. This is where we find the period of the function mod n, and this is a non-deterministic kind of quantum magic. A number of qubits obviously affects the precision, but that's, Shor's algorithm. Again, people often come up and say, okay, well, that's the thing we talk about when we talk about security. Now, they also talk about quantum breaking that, and I would tell you that, let's say, and this is not an actual real engineering example, but let's say, for example, that 100 qubits could break using Shor's algorithm, RSA. Well, then you would probably just make your key link longer, and actually would increase the complexity of the problem, and now maybe it takes 300 qubits, and maybe that actually takes us a few years to get to. Security is a journey, not a destination, and so threat and remediation often advance together, where you have a bigger threat, you build a better remediation, and then the threat gets bigger again and again. So when you look at using this for cloud computing for cryptography, it's not just in using quantum computing to make a cryptographic algorithm, it's also in things like quantum communications, where you use entanglement to actually do the communication over the cloud. Now, one question I see here that's tied on, both one from Tom Veroff and one from David Alexander, is um, to what extent is the intention to cover quantum cryptography with these standards? In the nomenclature standard in 7130, we'll absolutely be covering terms and use of terms related to that. In benchmarking, it is something that has been discussed but not settled on. And Tom, if you'd like to join us or email me and have a discussion about that, I'd be more than happy to discuss that with you. David, in regards to your question, will the IEEE develop standards for post-quantum cryptography? Yes, in that same aspect that I just spoke to Tom's question, we will be looking at the quantum cryptography and also post-quantum cryptography and how that affects both the nomenclature and both the testing. The testing started for quantum computers, it moved into the software, and then it is naturally moving into the cryptography.
Looking at the Google Trends, what exactly was the spike in 2016?
So in 2016, if you look at Gartner's hype cycle, if you look at everything else, there were several developments that led to basically a lot of press and a lot of interest, and therefore a lot of Google searches on it. You had announcements from D-Wave, you had some announcements from various government efforts, like the flagship effort in the EU coming up, and so quantum computing kind of had that peak around there, and there were some pretty interesting developments, and just a lot more. There's some investment in quantum computing companies as well, and I think you see definitely a correlation of when Silicon Valley makes investments in a technology, and there's some news on it at the same time. That kind of being a big generation of hype and more news, and then that begets more searches, and that begets more people wanting to write about it because people are searching about it. And I think that's what you see that really big spike about. I think you're going to see in 2017 and 2018 that kind of normalize out as we're starting to get people to really come into a more of a realistic view of the technology, because now there's 4, 5, 6 machines that you can play with online. There's a lot more questions being asked, and so I think you'll see things kind of come out of a hype cycle in the more level, metered, measured approach.
Okay, thanks. So at a current trend, at the current trend right now, when do you think the RSA encryption could be cracked?
Oh my gosh. So again, so this is the fear and uncertainty and doubt that I want to try to be an evangelist and a champion for clearing up. So I think it depends on the type of architecture being used and the type and the number of qubits. It could take millions of topological qubits for all we know. I think there are many people working on this, and I think it eventually will be cracked. But again, uh, you know, so I have a key length of a key. I get your public key. I'm able to then go through and surmise using quantum computing this order finding your private key. And so now I've broken it. Um, I don't necessarily, even at that point, have a repeatable process for breaking all encryption. So don't think of it as RSA encryption being broken. Think of it being able to break a single RSA key and then potentially going and repeating that process again and breaking another one. It doesn't quite work. It's not just like, okay, RSA is broken, game over, now I have access to everybody's stuff. More than likely, it's very difficult to break RSA for a single instance. And then when you change the instance, you change enough of the factors that it might increase the need for a number of qubits, the fidelity system to break again. I don't think this is something to be concerned about. I think it is something the press likes to write a lot about because it's clickbait. When you talk about, oh, everybody's encryption will be broken. I think there's already post-quantum encryption efforts going on. I think there's already companies from Cisco to IBM to everybody working on these resolutions. And I think there's also simple practical solutions in increasing key length, et cetera, that increase the mathematical complexity. So maybe if a 100 qubit machine breaks it, maybe I now need a 1,000 qubit machine. And so you've just bumped that down the road. I think that's how security works. I think it's very, very important for us to understand how security works. It's not like we've broken the encryption, everything's done, or we've built a new security, it'll never be broken. It's not really how that has worked in the entirety of computer science, and it will continue to be this emerging, evolving threat and remediation, entwined in this dance that changes, and the pendulum swings back and forth to hackers have an advantage. Okay, the advantage has been taken away. Okay, now they have an advantage again. So, if I venture to guess, I would say the first system to break it would be a circuit gate model or topological system and not an annealer. Um, I say that for, various reasons. And I think that machine probably has to have, a few thousand qubits. And again, it might need many more than that. I think that's a very good question. I wish I could give you an exact solid answer or prediction on it, but there's a lot of factors in there.
Thanks. Let's kind of move into back to IEEE standards. So one person is asking, will P7130 account for an emerging alternative to quantum computing model, for example, annealing combined with a gate model?
Sorry, which question is that?
If you're looking for it, it might be hard to find because some people are coming to me privately with questions.
Oh, okay.
So, yeah.
We'll give that to me one more time then, because I am looking for it.
I will send it to you as well. But will P7130 account for an emerging alternative to quantum computing model? For example, annealing combined with a gate model.
That's a great question. We have not had that discussion, but it's definitely something to take in effect. Again, the focus is on quantum computing, so a combinatory model, yes, but we probably wouldn't cover things like um, you know uh, uh, neomorphic or other computing, exotic computing architectures. I think the question there is very astute in that, there will be ways to potentially combine some aspects, but I don't know that you would actually combine the systems in that way. So I don't know that you would have an annealer. I mean, I guess you could pre-process data on an annealer and then somehow take that back out to a classical system and then put it back in. But remember, in that case, you would have broken the model that we're trying to develop a standard for, because we're only trying to develop a standard for the performance of running that algorithm on that quantum computer. Much like entanglement, the reason entanglement is not faster than light is once the classical component comes into it, well, then everything slows down. So it would dramatically increase the complexity if you looked at a chained system. So we're looking at when you get the data from the classical computer into the quantum computer, how you're getting it in. Is the solver optimized? Is the solver on the comparable classical system optimized in the same fashion, et cetera, et cetera. But that's definitely a very interesting point and something I will take into account.
And you might have just covered it, but how does the P7131 measure performance? It says it seems
So
to
this is
depend
something
on an
we
algorithm
haven't.
it uses.
Yeah, yes, it will. It will actually have to have, it will have to have a specific use case, and that's the discussion that the working group has been having right now, is how do we determine what case, or in reality cases, we are going to use to do that. So it will be dependent upon an algorithm, them running the same algorithm. It will also depend on solvers and them having the same solvers. So one thing that's been proposed is that we might also, alongside the standard, have a group that open sources a solver that can be easily modified to be optimized for different classical compute architectures, and potentially a baseline solver for these three quantum computing architectures. So it's a very good question. It is very dependent upon that, and that is something the group has been working on and trying to determine the best way to come up with an objective way to get a performance benchmark on these architectures.
Can individual IEEE SA members join the working group, or only corporate members? And as well as how can research institutions like a university get involved as well?
So if you're in a university and you want to get involved, simply reach out to me and I can help walk you through that process. It's a little different for universities. If you are an individual, then you do need to come into this particular standards project through a company or corporation.
Thanks. Do you see benchmarks around particular algorithm families?
I think, yes, I do, but that's something, again, that's in discussion in the group. But I think that there will be certain things that will lend themselves very well, certain areas that will lend themselves very well to benchmarking, and I think there will be certain things that will not lend themselves very well, and therefore they might have to be broken down into sub-problems.
I sent you privately our next question, but how do you propose benchmarking a quantum computer if it can solve problems that a classical computer cannot?
Okay, so this is something that kind of that's it. First of all, that is a great question. I wish that person would have asked it out so I could call them out by name and thank them. That is a fantastic question. I don't think it's an issue. Let's take, I don't, this is super great question. I hope everybody is paying close attention. It is not a question of a classical computer not being able to solve a problem. It is a question of a classical computer taking forever to solve that problem. Allow me to explain. If a classical computer were to do a traveling salesperson problem, right? Michelle Simmons, awesome person, physicist working in quantum, I'm a big fan, often gives the example of a traveling salesperson. So if you have a computer that does 10 to the 9th operations per second and you want to send a salesperson to 14 cities, it's about a 10 to the 11th problem, and it takes that computer about 1,000 to 1,600, seconds to do that problem, okay? And if you increase the number of cities to 22, that same computer, the problem goes from 10 to 11th to 10 to 19th, that the same computer takes 1,600 years. Okay? And then if you go to 28 cities, then it takes longer than the time of the known universe. So don't think that this is a question of, oh, these classical computers can't solve. When we say they can't solve them, it's a matter of they could solve them eventually. So when we talk about benchmarking a quantum computer, there are a ton of problems and a ton of examples and algorithms that we can show what is being commonly called quantum supremacy on right now to use as baseline benchmarking. So again, it's not a matter of the classical computer necessarily not being able to do it, it's the amount of time in which it takes taking forever. And obviously in some of those cases, it would be obvious that, the computer, classical architecture is useless in doing that problem. But one of the things that bugs me is often the kind of devaluing of the classical computing systems when we talk of quantum computing. Look, I am as excited as anybody else, about quantum computing, but that doesn't mean I don't appreciate the classical architectures or their role in quantum computing, or the fact that, we need them to perform quantum computing. We're simply talking about in the performance benchmarking, um, trying to figure out how we can show that this new technology, this new process of solving some, running an algorithm, solving some mathematical problem is actually better in a way that industry can guide itself to say, okay, now we're comparing apples to apples when I look at what IBM says versus what DOA says versus what Rigetti says versus what Microsoft says. But it's a fantastic question. But again, I don't approach it from the standpoint of, oh, the classical computer just can't do it. We say it can't do it because it's impractical. But there are tons of things that classical computers right now do very much on par with where quantum computers are. And so we need a benchmarking standard both to denote that point in time where we can actually prove that superiority and to be able to compare apples to apples moving forward.
So how far along are the performance standards discussions? Did you begin with the MaxCut/Shor's algorithm or something else as your starting point?
So that's a great question again. We are just now starting that, and yes, we're looking at what's called the commonly referred to as the quantum zoo, which is a collection of a bunch of quantum algorithms, and then looking at what would be the best to start doing benchmarking. And we do want to have several of those that we take into the standard as we create a starting point. But remember, this group literally just formed, and this particular proposal is fresh, hot off the presses. So would love to get, John, you involved in that based on your question, should you get your company to be able to come into this, because that's a very good question, and that's a process that we're going through right now. So the answer is in process, looking at all of those, not sure whether we use like a MaxCut or a Shor's or whether we'll have our own starting point. I do believe that using a commonly accepted or several commonly accepted things like Shor's algorithm that can't really be tweaked or modified will probably be the shortest path to doing something like that, although there has been some interest in creating an algorithm specifically for benchmarking.
So cryptography.
In regards to cryptography, yeah, I'll read it. If there is a new crypto standard candidate found by the IEEE, would IEEE search for standardization via ISO or IEC? That is a great question, and I would have to cross that bridge when we get there. I don't know that we would be creating a new crypto standard, but I know that the IEEE does collaborate with other standards groups, and that is a conversation that we've had in this particular area. So, that would be kind of a to be determined thing. It would be very exciting if we did that. And if we did it, I would want to see it be adopted by others.